So I decided to talk about this topic. I apologize with those of you who already heard this talk in last August in Cortona, but I think that it was fitting very well the theme of this workshop. So it's a joint work with Andrea Merlo from last year, and it's about the endpoint Fourier restriction and unrectifiability. First of all, let me give a brief overview. I will also, so let me say that I will try to guide you through the proof as well of this result, because it's not very long. So I will try to stay very basic, and I will explain all the things that we will encounter. So I apologize also if it will be a bit too basic at some point. So I will start by recalling what is the restriction, the Fourier restriction problem. And then I will give the statement of the main result. And then, as I said, we'll try to guide you through the proof. We'll need two tools, namely from GMT, namely the decomposability bundle and tangent measures. And then I will give you the proof of the main result and discuss some possible future directions. Okay, so let me start by recalling the restriction problem. Well, we start from a function from Rd to R, and we define as usual, the Fourier transform. And the Fourier restriction problem asks the following. If we are given a surface S, when can we restrict, when does it make sense to restrict the Fourier transform of F to S? And more precisely, this means for which exponent P and Q between 1 and infinity, we can find such an inequality, which means basically that the Fourier transform is continuous as an operator from LP over D to LQ of the surface, of the given surface. And this question, of course, makes sense if we replace the surface with the general measure mu. And so we ask when we can find such a continuity property between LP over D and LQ of mu. And we say in this case that mu admits PQ restriction, and we indicate it by this symbol. So the restriction holds for the measure mu from LP over D to LQ of mu. And a totally equivalent formulation for this is given by the extension estimate, which is this one here, and it will be important for the following. And it's saying the following. So it's completely equivalent to say that if we fix any test function G, we consider the product G times the measure mu, we take the inverse Fourier transform, then we can bound this in the dual norm LP prime over D with the original LQ prime norm of mu. Okay, so let me start with some examples. So the restriction always holds from L1 to L infinity, because the Fourier transform of an L1 function is continuous with the bound on the sup norm. So this is the trivial case, it always holds, and for this reason we will always consider P bigger than 1 in the following. Then if we take as mu the Lebesgue measure, we know that the restriction holds from LP to LP prime by Hausdorff-Young for P between 1 and 2. And regarding some negative results, we have that the restriction from L2 to L2 does not hold for any singular measure, essentially by Plancherel, because we know that it is the Fourier transform is an isomorphism between L2 and L2 of Lebesgue. So basically, we cannot see any finer measure, so any singular measure. And also, as a negative result, we have that if we take a flat measure, so we take as mu the k-dimensional Hausdorff measure restricted to a k-plane with k strictly smaller than D, then there is no non-trivial restriction. So for no exponent strictly bigger than 1, we have restriction. And an easy way to see this is that it's easy to see it in one dimension. So for the delta 0, which is the zero-dimensional measure in R, for instance, considered by rescaling some Gaussians. And then we can consider tensor products, and because the Fourier transform behaves very well with respect to tensor products. Now, what about some positive results? Well, the most famous is maybe the sphere. It says the following. If we take the sphere in Rd, then actually there are some non-trivial exponents for which the restriction holds. And there's this result from LP over D to L2 of the measure by Thomas and Stein, but under this assumption on the exponent P. And this is known to be the best possible when the codomain exponent is 2. But in general, this is an open conjecture, one of the most famous in the field. And basically, it says that the conjecture, the restriction should hold for these exponents here. So there are two conditions. The first one relates P and the dimension only. And I'm not very interested in this now for the rest of the talk. Now, the second one instead is more interesting to me because it relates the exponents Q and P through the dimension D. And okay, other positive results exist for curved surfaces. So let's say for the paraboloid or the cone or surfaces with the positive Gaussian curvature. Now, I want to talk briefly about this condition here and how one can prove this necessary condition if we consider the spherical measure. So this is called the Knapp's example. And it's a quite simple computation that consists in considering a highly localized bump function in the extension estimate formulation. So I recall that, so this is the extension estimate formulation. We have to bound the, for a given test G, we have to bound the inverse Fourier transform of G times the measure with the original function G. Now we fix any bump function, say in the unit ball, positive, and which is 1 on a certain neighborhood of the origin, and we rescale it and we center it at a point psi 0. And so we make it supported on a ball of radius delta. Now, by the geometric properties of the sphere, this means that actually the support of this measure phi multiplied by the measure sigma will be contained in a spherical cap, which is of length delta in all directions except for one, but the thickness will be delta squared. And so this means that if we explicitly compute the inverse Fourier transform of this rescaled phi delta times the surface measure, by definition it is this one, now we can bound this, this expression from below whenever we consider x in a dual box of size, basically the inverse. So 1 over delta in all the direction except 1 over delta squared in the last direction. Why is that? Because in this case, if we take x in this box and psi is restricted to this box, then the scalar product is essentially near 0. And so the exponential is totally negligible. So it's of order 1. And so we remain with the integral of the original function, which is going as delta to the d minus 1. Now you can, by scaling properties, you can compute the LP prime norm of this. And on the other hand, on the right-hand side, we need to estimate the LQ prime norm of this free scale bump function. This is, again, an elementary computation. And if we put everything together, we obtain the final condition relating P and Q. So it says that Q is less or equal than d minus 1 over d plus 1 times P prime. The power of this computation is that even though it's very elementary, it gives exactly the conjectured optimal range for the restriction problem from the sphere, so the open problem. Now I want to discuss a slight generalization of this this example to other settings that make the geometry somehow, that are based on the geometry of the measure. So first of all, we can consider a measure which is rectifiable of class C1 alpha. So it can be covered by countably many graphs of C1 alpha functions. Then we get, by the same computation, it's essentially considering that now the thickness, if we consider such a measure, at most points and at most scales, it will be contained in such a box where now the thickness is delta to the 1 plus alpha instead of delta squared. And we obtain a condition depending on alpha. And in particular, if you put alpha equal to 0, you get a condition for when mu is rectifiable, standard rectifiable. that says that Q is less or equal than S over D times P prime. So where S is the dimension and D is the ambient dimension. And in general, if we impose that mu is S-dimensional, so no restriction on the geometry, so we only ask that the densities are positive and finite, then we obtain exactly the same condition as for rectifiability. So basically, imposing the dimensionality of mu tells us nothing more than, imposing the rectifiability tells us nothing more than just the dimensionality. And I will be interested in this, in the endpoint exponent, which means the extremal exponent that can be reached by a measure mu of dimension S. So I will be interested in the case where Q equals S over D times P prime. And as I said, so using the information that the measure is rectifiable gives nothing more than just the information on the dimensional bound. But as we will see, actually, in the case where the measure is rectifiable, the endpoint exponent cannot be reached. So there is a strict inequality. And this is more or less the theme of the talk. So look at the endpoint case where the exponents are these ones, so Q equals S over dP prime, and try to understand something about the geometry of the measure which satisfies such an extremal restriction. So let me first mention one positive theorem. So a case where there is existence of a measure mu of dimension S, which is, say, upper S regular for certain values of S that are basically sub-multiples of the ambient dimension, and for which the extremal endpoint restriction holds. So there are these examples due to Schmerkin and Suomala and Chen-Seeger that show that at least there are some examples of measures that satisfies this endpoint restriction. And curiosity is that if the measure is also lower regular, then the restriction cannot hold at the endpoint. And this is, if you want, an indication that imposing the endpoint restriction tells us somehow that the measure cannot be too regular in many different ways. And in particular, if we look at all these examples, they are fractal. They show a fractal structure. And so the main result that I want to present is the following. It goes in this direction and tells that if we take a measure mu on RD with positive and finite upper density, and so no requirement on the lower density, we suppose that the restriction holds at the extremal exponent. So for some p bigger than 1, and for q equals S over D times P prime, then we have a dichotomy. Because either on one hand, we have that the exponents are dual to each other, and as a consequence, the measure is absolutely continuous, or the measure mu must be at the total opposite of the spectrum and must be supported on a purely one unrectifiable set. So even for any dimension S, still the second condition is saying that the support is purely one unrectifiable. And so this shows in a way that the already known examples of measures satisfying the endpoint restriction had to be fractal in a way, so had to be purely one unrectifiable. Okay, so now I will try to explain the proof of this result. I will first recall what are tangent measures. So just to set the notation mainly. So if we take an S-dimensional measure mu, a tangent measure is any non-zero Wixter limit of the rescalings of mu around the fixed point x for a certain infinitesimal sequence of radii Ri, and rescaled by Ri to the minus s. Okay. And why I'm talking about tangent measures and why are we considering the endpoint conditions on the endpoint exponents? This is because exactly in this endpoint condition here, the restriction is stable under blowups, so it passes to tangent measures. What I mean is that if we start from a measure mu that has the satisfied restriction for the endpoint exponent, then any tangent measure will satisfy it as well with the same exponents. And this follows from a simple scaling of the Fourier transform and of the LP norms. And so we can immediately see that if we have a rectifiable measure, then it cannot admit endpoint restriction. Why? Well, because a rectifiable measure has only flat tangent measures, mu almost everywhere. But we know that flat measures do not admit endpoint restriction. And so this stability property means that then the restriction would have to hold for the tangent measures, so it cannot be that they are flat almost everywhere. And the general result will be a refinement of this, basically of this proof here, that look at some finer properties of the measure expressed in terms of the decomposability bundle. So what is the decomposability bundle? It was first introduced by Alberto Marchese a few years ago, and is the following. So we start from a measure mu on Rd. The decomposability bundle assigns at mu almost every point x a subspace V of mu x, which is the maximal, in a way, linear subspace, such that if we take any Lipschitz function from Rd to R, then this function is differentiable along this subspace V mu x for mu almost every x. So it's a distribution of planes of different dimensions defined for mu almost every point. And there are many different equivalent characterization of the decomposability bundle. One which is maybe even more geometric is the following. That says essentially that V of mu x is the subspace along which we can decompose the measure in one rectifiable measures in that direction. And I will, so just to briefly state a few known results. So we know that if the decomposability bundle is the full space Rd for mu almost every point, then the measure is absolutely continuous and vice versa. And this is essentially in a way related to Rademacher's theorem. On the other hand, if the decomposability bundle is trivial, so is zero at mu almost every point, then the measure is supported on one purely rectifiable set, and also vice versa. And in particular, one of the equivalent characterizations which is very useful is the following. So we have that for mu almost every point, a vector V fixed belongs to the V of mu x, if and only if we can find a vector value measure sigma, which is divergence free, and that approximates the measure V times mu at small scales near x. So we start from the scalar measure mu, we multiply it by the constant vector V, and then we ask to find the divergence-free measure, vector valid measure sigma that approximates at small scales this V times mu. Okay, now why is this useful? Well, because I recall this fact here, that so if we take a measure mu on Rd, then for mu almost every point, we know something about the structure of the tangent measures in terms of the decomposability bundle. Because we know that any tangent measure eta that we take will be invariant in the direction of the decomposability bundle at the point where we are taking the tangent measures. So this means that if we take a tangent measure eta, there exists a random measure theta on the orthogonal of this of the subspace V, such that theta is the tensor product between theta and the flat measure only. And okay, the proof of this proposition is it's quite simple. We fix a point x in the support. We take any tangent measure which has the following form. Then we take any vector in the decomposability bundle at the point x. By the characterization that I told you the last slide, regarding divergence-free measures means that we can find such a divergence-free measure sigma that approximates v times mu at small scales. But then essentially plugging in the definition of tangent measure, we obtain that, okay, I'll skip the details, but we obtain that essentially we find that the tangent measure eta multiplied by the constant vector v has divergence 0. Now this means essentially that v times eta, that eta is invariant in direction v. Now this holds for every direction v in the decomposability bundle, so we obtain that the tangent measure eta is invariant along all the direction of the decomposability bundle, and then we can conclude by disintegration and Hausdorff's theorem. So we obtain that any tangent measure eta is the tensor product of the flat measure on the decomposability bundle times some other measure. Now, a second lemma that I will use is the following. So it relates the Fourier restriction and tensor measures, and says the following, that if we consider a tensor measure eta, so theta times a flat measure, for where we have the flat measure is on a k-plane in Rd, we suppose that the restriction for this tensor measure holds between Lp and Lq for some exponents p and q. Then we have a dichotomy. So either k equals 0, so the flat measure is trivial, it's just a delta, so eta is just theta, or the exponents must be dual to each other. And the proof again is it's quite simple, because we just need to test everything with tensor functions. So with functions which are the product of two functions depending on the variables on either v or v perp. And again, I'll skip the details, but essentially plugging in this product of functions gives us some information, because both the Fourier transform and the LP norms behave well under tensor products by Fubini. And so we obtain in this way that if we assume that the restriction holds for a tensor measure, which is the product of a flat measure and some other measure, then it will hold for both factors. And in particular, since this holds we obtain this inequality here, that means that the ratio inside here, so the ratio between the function f in LP of the flat measure and the Fourier transform, the LQ norm of the Fourier transform in the same measure, has to be bounded. But then we know basically from the result in Rd, in Rk, that either the exponents are dual, or we need to be in the trivial case where k equals 0. Now we have all the ingredients for the proof of the main theorem. So we start from a measure mu of dimension s in Rd, and we assume that the restriction holds for at the endpoint for the endpoint exponents. And then I recall we must prove that either the exponents are dual to each other, and then in that case the measure is absolutely continuous, or mu is supported on a 1-polar unrectifiable set. So first of all, for mu almost every point x, we can take a tangent measure also, and for every tangent measure eta, we know from the stability under blowups of the restriction, the Fourier restriction, that the restriction holds also for the tangent measure eta. So eta still has the same restriction for the endpoint exponent. But on the other hand, we know from the characterization through the decomposability bundle that tangent measure eta is the tensor product of some measure theta and the flat measure on v of mu x, the decomposability subspace. Then, from what I told you the previous slides, we deduce that since we have a restriction for a tensor measure, we are in two cases. So either we have that P equals Q prime, and then necessarily if this is if this equals if P equals Q prime, we have that S equals D, so the measure is absolutely continuous. Or on the other hand, K equals 0. But this means that for mu almost every point, since we can do this for mu almost every point, this means that the measure must be supported on a one purely unrectifiable set. Why? Because we proved that the decomposability bundle V of mu x has to be trivial, so it has to be 0 at almost every point. And so by the characterization of one unrectifiable measure by means of the decomposability bundle, we can obtain the conclusion. Okay, so to finish, let me just mention possible future directions. So this is a work in progress still with Andrea Merlo. And the idea is to use similar techniques to say something about other measures, other good measures, satisfying other types of good properties. So this has been mentioned in the previous talk. It's a very old problem. So we consider a measure mu, and we suppose that the Ritz transform is bounded in L2 of the measure for a regular measure, so of dimension S. Then the conjecture that we already seen in the previous talk asks whether, under such assumptions, the measure mu is uniformly rectifiable, at least rectifiable. And so I mentioned this just a few names here. So this is known only in the case of dimension 1 or codimension 1, basically. And there are general results that that regard reflectionless measures by J and Nazarov. But in general, the conjecture for dimensions in between 1 and D minus 1 is not known. And so the aim in this case would be to basically use the decomposability bundle and similar argument to say something about possible counterexamples to the conjecture. So the conjecture, of course, says that there is no counterexample to this, but at least we'd like to show that if such a counterexample exists, then it must have a very singular structure. Namely, if we consider a sort of minimal, a counterexample of minimal dimension, then it must be purely one rectifiable. So the aim here is to use, again, to go through the decomposability bundle to prove such a restriction on possible counterexamples for this conjecture. And again, I say that, I mean, starting from any dimension S, it's sort of simple to show that the counterexample should be S purely rectifiable, but the point here would be to reduce the S to 1. So to prove that actually this possible counterexample cannot be seen even by one Lipschitz curve. Okay, so I think I told you everything I wanted to say, and I thank you for your attention.